as it was announced, it's about some spectral problems for differential operators with operator coefficients. I want you look at that differential expression that you see on screens, 1.1, that formula, that one, and that expression is considered in that space, in that functional space. Just for reminding some facts from here, I think everyone knows about it. Just for reminding, as you see, in my expression, it was fourth order like that, and coefficient differs from ordinary differential expression in coefficient. A here is operator coefficient, and another operator coefficient is qt by y. All y's taken like that. And space L2 H01, as you know from Leon Smajan's book, these are spaces of functions, vector functions, yt. Here H is abstract Hilbert space, separable Hilbert space. For each t value taken from that interval, our function value is from space H, from here. For example, it might be if in place of H stands another L2, say L2AB, then that space turn out to be L2 and on Cartesian on that rectangle by Cartesian product with 0, 1, such kind of functions. And as if function depend on two variables, and for each t fixed t, your function as function of x is becomes from L to AB, like that. It is just about definition of that space. And norm, about norm. Norm, you know, here I mean in that space, it is given by mean of in the next way from 0 till 1, and that functions square norm in H. In H, for example, here from that space dt. If I will consider that example that I have shown here, if I will take functions from here, then it just simply turns out to be from 0 till 1 and from A till B, and now it becomes modulus ytx squared dt dx. Yes, these are well-known facts. Just I want to remind it. Okay, turning back about coefficients. I said A, it is unbounded operator coefficient. Qt is bounded. So it might be if I'm considering, for example, if that space again in that example by 0, 1. For example, if the first differentiation goes respect to t, second might be, for example, another differentiation operator y's derivative with respect to, say, x, if x changes in AB, if x changes in AB, second derivative. So it is differentiation operator. A is differentiation operator. Yes. Qt, it is a bounded operator. It might be some multiplication operator. It might be integral operator, and so on. Okay. On coefficients, surely we have some restrictions, like A is self-adjoint as well as Q. Else L inverse positive definite operator, and its inverse compact. Under that conditions, it is well known that operator A's spectrum will be discrete, so it will consist only of eigenvalues of finite multiplicity. Geometric multiplicity is meant here, with only possible limit point at infinity. Okay, now our aim was to just okay, look, we introduced the new space, that direct subspace, as if we exit from the previous space, from here, and take this direct sum with H2. H2, it is copies of H, that separable Hilbert space. And here, surely, new scalar product is defined. Surely, now that scalar product will be in first terms of these elements, as you see in yt's, and That's triple, in fact. Why it is down? Because it's mainly case for problems when you consider some eigenvalue or boundary value problem with eigenparameter in equation as well as in boundary condition. What I mean, just in simple case, consider the next one, the next eigenvalue problem, lambda y. I mean just L201 scalar case, not vector functions case, and some boundary conditions you can put. Let it be Dirichlet conditions like y of 1 equals 0. Here you know that when you want to associate operator with that problem, what you do, you take a function y t whose first derivative is absolutely continuous, in 0, 1, and moreover, if that differentiation denoted by Ly, so that Ly, that differential expression, that one I mean, is from L2, and also for that functions from domain of when you define operator from domain that condition for functions from domain that conditions are satisfied, and so your when now you can write it in operator form like lambda y. What you mean under L? You mean second 2 times differentiation, that one, and domain is what? Domain those functions yt's for which all that three are held. But when lambda parameter, eigenvalue parameter, included also in boundary condition, in one of the boundary conditions at endpoints. For example, if you have the next problem, just look, minus y's double derivative equals lambda y, and you have y0, let it be simple case, equals 0, and the next one I'm putting y prime y equals lambda y1. In that case, if you wish to write it as lambda y, lambda y equals lambda y, in remaining in previous space, I mean remaining here, you can't do it because anyhow you will see that your functions from domain, they will satisfy some condition depending on lambda, so it will depend on lambda here. But you can do it without lambda, without that. How? It is said to be a linearization technique, and it is well known for scalar case, as well as for partial differential equations, as well as for differential equations with operator coefficients. For scalar case, all authors mainly refer to works by Fulton, or by Voltaire, that works as original works. But what is this? What is the subject here? You have to exit from that space. You have to consider direct sum. That's such a direct sum. So from previous original space, you have to go to bigger space, that direct sum space, and here C is complex space, that one. Why? And your function, your operator, even your function, is not just yt, it becomes two-term vector. The first term is yt, second term y1, where y1 is element of that space. See why you are doing. And further, that in place of y1, you should take y1. So instead of yt from previous definition, you should take yt and y1, such a vector, two-component vector you should take. And now your operator on yt and y1, it will act like that. Minus y second derivative and y prime 1, as if that y and that one are taken to form the new vector, as I put it here, you see from here, and your operator on the first term acts like that, and on the second term it acts like that. When doing that, you can form that eigenvalue problem, right in a linear like that, Ly, without any lambda here. It will not depend now on lambda. By that, as if you a bit make conditions on domain, on vectors from domain of L a bit weaker, as if you don't put that condition. How domain is defined? Domain defined in the next way. One moment. Okay. You just should take. You shall take a domain of Y, domain of L. It consists of those two component vectors, where Y, Ly, say so, it's from L2, and Y 0, say 0, and you miss the second condition. Do you remember which condition? Condition where lambda was involved, where lambda parameter is involved. You don't put that condition. You define your function, your operator just like that. But when you come to eigenvalue problem, when you put that one, Ly equals lambda Y, that condition anyhow, that can Y prime 1 equals lambda Y1, it anyhow it is involved here. It is involved here. So that operator writing, it completely involves bound eigenvalue setting like that.
Yeah.
I just said that when you consider some eigenvalue problem with lambda involved in boundary condition, for each I write that problem lambda Y, and I put here that boundary conditions y0 equals 0, y prime 1 equal lambda Y1. You see same lambda appears here also in equation and in boundary condition, and your space is that one, say 0, 1. And when you know, if you stand here instead of lambda some real parameter like y prime 1 equals h y1, you can simply associate with that problem. I mean that one, that problem, that one, also that one. You can simply associate with it some self-adjoint operator. How to define it? Its domain of definition consists of those y's who first derivative absolutely continuous on that interval, and second derivative it's from L2, and also that conditions, boundary conditions, y0, 0, y prime 1 equals h y1 satisfied. But when lambda involved here instead of real parameter h, you know that in no way you can't associate with it, with that problem, self-adjoint operator remaining here, remaining in that space. But one can do it by exiting from that space. How to exit? By constructing the next direct sum space that C is complex space. In here, you can do it. One can do it. That techniques are known. I said that formally for scalar, it's studied in for scalar case, for differential partial differential equation, as well as with operator coefficients. For scalar case, the authors mainly they refer to works by Fulton and Walter as original works, by Fulton and Walter. Fulton and Walter's different works, but I have to tell you that work refers, I think it was 1976. But for partial differential equations, for example, for Laplace equations, even when lambda included in equation as well as in boundary condition, consideration of problem in exit space, in broader space, and associating with it self-adjoint operator in that broader space, that methods were laid by Odnoff, for Laplace operator in 1959, and by Schechter and Ercolano, for higher order, for 10th order elliptic type differential equation in 19 and 65. Okay, so just why I put that dates here, just to show that for partial differential equations, such consideration and that techniques were offered even far before scalar cases. Okay, what's the problem here? Why you can't associate with that one self-adjoint operator? Because, for example, just when considering again that one, what means self-adjointness? You consider adjoint operator, we'll call it that, and if you will write Green's identity minus y L star. By L star, I mean if L operator associated with that problem, with that one and with that one, without lambda. Then L star, by L star, I mean, okay, adjoint operator. Okay, in Green's relation, you know that yz, its values at one endpoint minus its values at another endpoint. And self-adjointness obtained when that conditions at boundary conditions makes situation such that that becomes zero. But let's just consider in simple case. I mean, let's take, for example, let's delete all that. I just want to clear why, what is the sense of why we go out from that space. Again, I'm considering Ly, let it be minus series double derivative. Firstly, I'm taking it to 0, let it be y prime 1 equals h of y1, h, a real parameter. When performing that integration by parts, I mean that Green's relation, Ly by z dt, when performing that here stand conjugate of that, you know that what appears, what we get here. First, it will be a first derivative at 1, and that's first derivative at 1 is conjugate, and plus y prime 0, and that's conjugate at 0. Another integration by parts will give you the next ones, y at 1, and that's derivative at 1, and minus y at 0, and that's derivatives at 0, and minus integral plus integral from 0 till 1. Now y L over z. That one, you will come to that one. Okay, y0 z0 makes that two terms 0. About them, that boundary condition when h is real, from here you see that what you'll get, instead of y prime 1, you might put h, y1, and z1. Same thing here, because when you will pass to conjugates, z's and y's are from domain of definition z of 1, sorry, z of 1. When you will pass to conjugates, because of h is real, you'll get again h here. And from here also will go out h, you'll get y1 and z1. That two terms also will take it, will eliminate each other. So self-adjointness will provide it in case of real parameter h. But when instead of h here stands some lambda, so your equation is lambda y. Also, the first boundary condition say y0 equal 0. The second is y prime 1 equal lambda y1. In that case, because lambda is in general, it might be complex number, so it will not provide your self-adjointness of your operator. But it was known that you can do it by going to exit space, by exiting from space, by if you will go out from that space and you will go to that direct sum space and define here new scalar product, and instead of one component vector, you will consider two component y2, y1, as if y and this form the functions from domain, and application of L on that vector. When it acts on that, it results in that one, y prime 1. When doing that, since you can firstly linearize your problem, it is said linearization, you can write it equals lambda y, here L will not depend on lambda now. In that case, you can do it. It is a linearization technique. Moreover, adding a scalar product in the second term, so adding scalar product in the space, it will eliminate in Green's formula that I demonstrated before that, values of functions at endpoints at once, that eliminating lambda. Adding that term will eliminate that lambda, and again you can in that new space really get self-adjoint operator. I have to tell you that even in general case that theory was laid down by Naimark and Crane. It is said to be self-adjoint or symmetric extensions of minimal operator with exit from space. Further, in several works, series of works by Strauss, he considers that problems. In our days also that kind of problems are considered, and they note in their works that direct application of that problems to differential equations, I mean which problems with exit, self-adjoint extension with exit from space, the application of that general theory to differential equations, they namely give a rise to differential equations with lambda dependent boundary condition. So it is really natural that you have, if you wish to associate with your problem self-adjoint operator, you should go out to broader space. We add that direct sum, you see. Now, in place of C, in our case, here comes H, that abstract separable Hilbert space, because our function for each T, it is from that space H. That's why. And we have triple. In fact, H to H4, how many H should be here? It depends on number of lambda of boundary conditions involving lambda parameter. Boundary conditions involving lambda parameter. Our aim was consideration of that problem. Just look, 1.3, 1.5. Fourth degree and lambda parameter included into conditions in that one and in that one. That's why H2 is needed. Even lambda might be surely even polynomially or included in boundary condition, or some fraction on lambda, some rational function depending on lambda. Then that copies number of copies of H, that number 2, it depends on that lambda dependent boundary condition, on that number. Also on, if polynomial is included, on degree of polynomial it includes it. So it varies depending on that things. But to be honest, that problem, in fact, it was studied by what was studied. Say so. It's self-adjoint extension and compactness of resolvent, so discreteness of spectrum. Because compactness of resolvent, it is well known that it provides discreteness of spectrum. By Olenek, by the next author, I just want to demonstrate it at the end. Just look by that author, Olenek. But I see there, formerly, my aim was to refer to his work, for example, for compactness of resolvent and self-adjointness of operator, and do some study some other problems. Which kind of problems? To study, say, self-adjoint asymptotics of eigenvalues, eigenvalue asymptotics, or eigenvalue distribution to set. Also regularized traces, evaluated regularized traces. But when looking at that work, I see that some mistake. What I mean, firstly, when after defines his operator over smooth functions at the beginning, minimal operator when defines over smooth and finite functions, he states that in that new space, closure of that functions results at that boundary conditions, which is impossible. Because even in scalar case, it is well known that when you consider finite and infinitely many times differentiable functions, for example, in L2, their closure will not give you some boundary conditions like that. It will give you just W2 for Sobolev space. Another mistake, in my opinion, it was about adjoint operator, so maximal operator. Again, he states that maximal operator, as if it is given by that boundary condition. It is also not case. Again, even in scalar case, it is known that for if your operator is second order differential operator, say so, and it is closer. At most, it might give W22 subspace, not boundary conditions like that. Okay, and also when proving discreteness of a spectrum, so other words, which is equivalent to compactness of resolvent, it was stated that it is for it is necessary and sufficient for all the three operators to be compact. But when I put it, I see that it is enough for cosine C to be compact. For remaining two operators, it is enough to be bounded just. And I have to tell you that if you consider that differential operator, even in 2n's case, in 2n's order, in order 2n, but without lambda-dependent boundary condition, it was started by Kochubey, Gorbachev and Kochubey in their joint work. But they consider it problems in remaining in that previous space in L2 without exit space, without considering that bigger space, without exit. Why? Because their boundary condition doesn't involve lambda parameter. Okay, that's why we have to consider, firstly, put down all, we have to write all that questions in detail. Firstly, we put down what domain of description, definition of domain of maximal operator, so adjoint operator. It looks like that. To be honest, it differs from Kochubey and Gorbachev's week by only in the next fact, by fact that G1 and G2 I take from that space. From a smaller space than in their case, because we are considering our operator here and our functions values at endpoint 1, just look at Z1 and also Z1, they should be from H. That's why you should put that conditions for G1 and G2. G1 and G2, you just look on them to be from that narrow space rather than from space with negative indices. H minus 1 over H. So this is a scale of Hilbert spaces. It is well known, generated by the operator A. Okay. So not too much things were down here. Just I put that two conditions with that one. The main thing that I did, it's involved in that theorem about when I put that for self-adjoint extensions to be discrete. Other words, for it is resolvent to be compact, cosine C should be compact. Other two operators, it should be, there must be bounded. And how it was done by writing resolvent equation like that. And when writing solution from 2, 9 into boundary conditions and putting everything, that solution of equation is that one, writing it into boundary condition, okay, and writing everything then in matrix format and putting it detailedly, we can see that that two conditions like that. This comes from boundary conditions. This equation, it comes from boundary conditions. It was enough just for cosine C to be compact. For others, it was enough to be just bounded. Okay, after doing, I passed to what? I passed to evaluation of asymptotics of eigenvalues and eigenvectors. Not eigenvectors, but eigenvalues. For it, we considered some special case of self-adjoint extensions, because self-adjoint extensions, I want to demonstrate it from that file. It's given by the next boundary condition, by that boundary conditions. You see, I'm where cosine C is self-adjoint operator. You know, self-adjoint operator. It is said that self-adjoint extensions given by means of that self-adjoint operator. It is also that here also exists. You should know, for example, even for in general case, in general theory in Neymark's book, it was said that self-adjoint extensions of minimal operator given by means of some unitary operator, which acts from one defect subspace to another. And why instead of unitary operator here comes cosine c, sine c? Unitary operator, it might be given by means of some self-adjoint operator c, because for self-adjoint operators they have very good expansion. Some element stands here, let it be h, till plus infinity lambda, spectral expansion. I'm writing just lambda over h like that. And if you have if you consider the next operator minus 2ic, it will be unitary operator, because it will be defined again by using that spectral expansion. Lambda here is real, and its norm when you evaluate its norm will be 1. Its norm will be 1. Norm of that operator is 1, so it is and it is unitary operator. That's why self-adjoint extension, self-adjoint operator C appear in that boundary condition here. So as if they replace that unitary operator. Okay. Okay, I said that I consider it a special case for it, taking c pi by 2 of I, c1 and c2 taking like that. Or if you will take it like that, and then write that boundary conditions for cosines and sines, you will come to that boundary condition, to that one. Okay, it will be simplified to that form. So in fact, I come to my original idea, to my original task. My original task was consideration of that form. So now I'm sure in it is discreteness of spectrum because of formal theory. I'm sure in it is being self-adjoint and so on. Okay, for when writing yt from the first equation, this solution when writing into boundary conditions, first and second boundary conditions, we get the next for the Fourier coefficients of unknown function yt, we get such algebraic such equation 3.12 or 3.13. In fact, I have to tell you that it is it's equation from which eigenvalues are defined. In scalar case, say in Neymark's work, when you have that characteristic determinant, yes, it plays role of that characteristic determinant. It appears that what are roots? We have to find these roots. Firstly, it can't have complex roots. We have to start from here. That's why. Because complex roots will result in complex eigenvalues for self-adjoint operator. It is impossible. That's why it has no complex roots, with exception of imaginary or of the form y plus minus iy, that kind of roots. But imaginary, it has also real roots. Real roots and imaginary roots, their behavior, the asymptotics like that. For real roots, we have that one. For imaginary ones, that one. And they both, but eigenvalue of our operator is first degree of z root plus gamma k. What is gamma k? Gamma k from here are eigenvalues of operator A. So our operator's eigenvalues form a sum of roots of that characteristic equation and operator A's eigenvalues. That one. So Z4 for Z1 and for Z1 it's the same. But as corresponding eigenvectors will be linearly independent. So to that root, to that eigenvalues, their geometric multiplicities are 2. When speaking about such kind roots, it has such kind roots too. Sorry, I have to answer one moment. Okay, for that root, so I first write that equation by using their power series expansion, Taylor expansion for all that functions, for sinus, for cosine, or hyperbolic sine and hyperbolic cosine, and you can apply then Descartes' rule of sines. And you know that number of positive roots is the same as number of sign change in coefficients of Taylor expansion. And from here we get that really such kind roots also exist, but its asymptotics is not big. That's why they, in fact, they don't affect asymptotics for lambda. That's why asymptotics of eigenvalues is eigenvalues defined by that formula, but with geometric multiplicity 2, like that. The next question of our interest was regularized trace. What is regularized trace? I want to give some information regarding it. Regularized trace, it's you know, when speaking about say linear operators on finite dimensional spaces, you know that what is invariant for them? Invariant is if A is Z matrix representation and lambda is parameter, I is identity matrix. Invariant is that determinant. It is, you know, nth degree polynomial if your operator acts on in n dimensional space. And when you consider for your operator, it is representation in different bases from that n-dimensional space, call it V. What is invariant? Invariant that for matrix representations, determinant such a polynomial, such a determinant of that polynomial, determinant of that matrix, and which is nth degree polynomial. And it's one of the for that polynomials, one of the coefficients. Before one of the coefficients, where I can write. Sorry. One of the coefficients constant term. So coefficient lambda 0 at lambda 0, and as it appears, it equals to sum of diagonal elements of matrix representation, and it doesn't till n, and it doesn't depend. It doesn't depend again on choice of basis. For each matrix representation of linear operator, finite dimensional linear operator, that sum of diagonal elements of this matrix representation, it is invariant, unchanged. And in case if operators eigenvectors orthogonal or all eigenvalues different, it gives you sum of eigenvalues. That sum of eigenvalues is said to be spectral trace, and that one, you know, it is said to be trace of matrix trace. Then passing to infinite dimensional spaces, say Hilbert space and so on. When passing to that infinite dimensional Hilbert space and so on, here the operators, compact operators, which with such property are called nuclear operators that have or trace class, nuclear operator or trace class operators. I just want to recall that these are those operators whose S values form convergent series. If your operator A is self-adjoint and positive, in fact, that S values turns to be eigenvalues. So when that sum forms is finite, it is convergent. Such kind of compact operators are said to be nuclear. And it doesn't depend on choice of basis in that space too. So if you have some basis, say phi i's, in Hilbert space H, I changing from 1 till infinity, then that sum doesn't change on choice of that orthonormal basis. It is always the same and equals to the spectral sum, to sum of eigenvalues. But when you can speak about unbounded operators, which are differential operators, you know, for example, if you consider that one, take some potential 2 equals lambda y, also take some, say, triplet conditions, let y of p let b equal 0. If you consider that one, it is eigenvalues under some differentiability condition on Q. Its asymptotics will be like that. It equals to n square plus c, mean value of that function potential qx. Okay, it is over pi like that, and plus some remainder part, which is 1 over behaves like 1 over n square. But when looking at that first term from the asymptotics, in fact, it is what? It is eigenvalue of the next problem. If you will take in place of qx 0, if you take qx equal to 0, it will be eigenvalue for that problem. Y0 equals 0 and y of pi equals 0. Okay, and it is eigenvalues will be mu n equals n squared. And in work, their famous work, firstly, Gelfand and Levitan, they consider it a name and a boundary conditions, that one. But then they considered Dirichlet boundary conditions, y0, 0, y of pi is 0. They evaluated lambda n minus n squared, mu n, and if you will put without loss of generality for that to be equal 0, you see that what remains here, 1 over n squared, which is convergent, which form convergent series, and it appears that it might be evaluated by means of potential. It equals to that to such some kind like that. So it is well evaluated, and that sum now is said to be regularized trace. So for kernel operators, lambda n or nuclear operators, it is trace, spectral trace, convergent. By differential operators, it is not convergent, but you can regularize it in which meaning? In such a meaning. And considering, say so, perturbed operator, perturbed, I mean, firstly, one time you consider operator with qx, another time when qx equals 0. So it's perturbation of that operator like that. It is obtained from here by perturbing, adding qx. So if you consider such kind too, operator and consider their difference of eigen values under some conditions on surely on potential too, you'll come to some say so convergent series which is defined by potential, which is that convergent series is said to be a regularized trace. It is said to be regularized trace. Too much works exist regarding the scalar case. I just want to remind one to tell you about one work when consider it say y of t such a problem lambda y and this such a conditions yp equals 0 and for that problem, regularized trace was aimed to study. It was studied in work by my supervisor's work, Mehmet Bayramoglu, in Daklat in 1980. It was published in Daklat of Academy of SSSR. And first problem here was what is regularization? What is lambda n? What understand under that? Because what to subtract from lambda, which terms should be subtracted from lambda, and because in comparison with scalar case, if you remember, I said that, for example, in the Gelfand-Levitan's problem, it was n squared plus c plus o over n squared, and it was clear that when subtracting that terms, you'll come to some convergent series. You can get it. But for differential operator equations, when writing asymptotics, you can write just the first term mainly. You can come to some terms forming that remain the part. That's why it was important what to call a regularized trace. In their work, they have shown that, again, they consider it that problem, and also case when Qt is 0, corresponding operators are called L and L0, operator corresponding to that one L, operator when Q is 0 denoted by L0. And they said it is the eigenvalues denoted by mu, and they stated that some subsequence of partial sums, if you will consider such a partial sum, lambda n minus mu, when the limit m goes to infinity, so that one is convergent. And it is said that that's why instead of a usual series, it is denoted by that symbol. That prime symbol means that subsequence of say so partial sums of that series converge. Lambda n minus mu n. Okay. In that work, when evaluating, they come to the next one. They see that it equals to the next sum, I from 1 till infinity, and also say k from 1 till infinity, q over phi I, like that, integral from 0 till 1 times cosinus to kx dx. They have arrived to that sum, which is in fact, if you look at it, you'll see that it is Fourier expansion. If you will consider just inner sum from here, k is here integers, k is integers, natural numbers. It's if that scalar product qx phi I by phi I, if you the scalar function denoted by qix, it's coefficients of Fourier expansion of that function qix in cosines. So from here they get that they first put it just in the one in the next form, cosine k times 0 multiplied integral from 0 till 1 qix and cosine kx dx plus cosine kp, again that integral. So you see that its values of that function at 0 and p. That's why it is obtained qi at 0 plus qi at pi, dividing by 4. And here comes also another sum from y to infinity. From y to infinity, it will give that trace. Okay. In my problems, when I consider, I just want to demonstrate you the next problem. Yeah, it's my work in 208. When I consider it more simple case, even second order operator, which differs from my supervisor's work from that. Second boundary condition at 3. It's published in Siberian Journal of Mathematics. It depends in second boundary conditions. Lambda is involved here. In their case, it was y of pi equals 0. When evaluating regularized trace, I see that I have come to the next sum, which is not Fourier expansion of anything. It was not Fourier expansion of anything. I come okay, say to that sum, say so, to that one. Here, xj, k, in their case, in place of xj, there stands k's, integers. But in my case, that x values, they are not integers. They are roots of characteristic equation, not that of that equation. It is not integer, some values. Some asymptotics were also found for that equation roots. So how to evaluate? So we can't anymore rely on Fourier expansion and so on. But what was done? Cauchy residue theory was applied here. Why? What was done? We selected some function of complex variable. For that function complex variable, I just want to demonstrate. I take that function, g of c, that. Numerator dictated by numerator of my operator, of my sum. You see that one, cosinus to xjkt and multiplied by 2xjk. Numerator is of that selected function dictated by that one. About denominator, for denominator, I just take roughly, I take characteristic equation. And I see that because you know that the roots of characteristic equation, poles of that one, and it appears that really, if you evaluate residue at its roots gives me that eigenvalues. It really, when evaluation, we get that it really results in terms of my series that I want to evaluate. It really results at that terms. Okay, applying that theory, we were able, we were able to evaluate that regularized trace. That method I further later applied many times for different problems, for high order problems, for problem having singularity at coefficient or taken over infinite intervals and so on. But when coming to that case, each time I take directly, roughly, my characteristic equation and put and see that I really get term of my series. But one moment from here, when looking at that series, that in that series to be evaluated, value of which I want to evaluate and which I call regularized trace, it's in fact norm of my vector, norm of my orthogonal eigenvectors. It gives, because of it's repeated each time, it gives me a sense that there exists some relationship between characteristic determinant and norms of orthogonal eigenvectors. Let's stop for a while that one and pass to my PDF file. Oh, if I can find it. Okay, you can see, yes? Can you see?
Yeah.
Just look at that eigenvectors, please. 4.1. They're so long, so big expression, and it is triple. It is vector three components. That one, and that one, and some sines, cosines, hyperbolic sines, and cosines included there. That time I don't know why that method doesn't work. I can't manipulate that method, and I think that it's time now, if really that connection exists, to put down it. Why it was impossible to behave as earlier? Because just look, it is so big expression you have for orthogonal eigenvector, and it's I just want to demonstrate you it is and its norm is like that. Just look at that 4.9, so big, where H's also are defined by some expressions. I mean that H ones from here. Okay, and I was able to do it here. Really, I take that's characteristic equation in our case. More general, it was taken, and it was shown that really derivative of characteristic determinant, say so. Do you see that theorem 5.1? Really, it gives you norming constants, CKJ's norming constants, the opposite norms of eigenvectors. So it gives a derivative of that characteristic determinant, give you norms of your eigenvectors up to that factor for that KJQ to that one. And after that, I was able to find my regularized trace. I arrived at my regularized trace. But before finding it, we have to apply it several times. And each time we see that the first application bring us to another boundary value problem, which is given by that boundary conditions. I just wanted to, by such a boundary conditions at 1, at 0 same, but at 1, so by such kind boundary conditions. One more application take us to such a kind boundary conditions. Okay, to that one. And finally, we come to the simplest boundary condition, to the regular boundary condition, say so in, okay, to that ones we come. No, it is not even final version. Okay, at the end we come to that one. Y0, y second derivative at 0, y value at 1, 0, second derivative at 1, 0. So for our considered operator, regularized trace appear to be equal to that problem's regularized trace. I want to tell you that it was also was seen also in previous works, because even when that work I have demonstrated from Siberian Math Journal, when evaluating it by, at the end we see that again we come to expansion, to Fourier expansion along cosine, okay, cosine along cosines. Okay, that one. At the end we get again expansion along cosines. Okay, and that more general case, which is in the case in my last work that I demonstrate in PDF file, that it should be like that. The fact that at the end we come to that boundary conditions, it means that yes, it was true. Really, you can't escape anyhow. You will come. You can work or manipulate your problem, and again you will come to more simpler boundary condition case. Say so. Okay, regularized trace evaluated, and my main formula is that one. Do you see several series? All of them are regularized traces for different operators given by different boundary conditions, to which I was followed by that method in applying it. Okay, that's it. That's all. Thank you.